The XR-DIVIN project applies mixed reality to improve accuracy in industrial assembly processes. Its objective is to align digital 3D models with the physical environment, reducing errors, rework, and costs. Current workflows rely on manual marking of structural elements, often outside the real installation, leading to inefficiency and risk of mistakes. The XR-DIVIN architecture is built on two components. A Python tool pre-processes and optimizes 3D models, preparing them for transfer. The core of the system is a Unity-based application running on the Meta Quest 3. This mixed reality environment enables operators to visualize digital models directly in the physical space, align them with real structures, and perform dimensional verification with precision. The computer handles file processing and transmission, while the headset provides an interactive and intuitive workspace. The Unity-based application, running on the Meta Quest 3, provides the core mixed reality environment. Its main functionalities include real-time reception and visualization of 3D models, recentering and fine adjustment of models to align with physical structures, measurement tools for dimensional verification. The following videos illustrate how these functionalities operate within the mixed reality environment. The Unity application receives 3D models transmitted from the pre-processing module developed in Python. These models, optimized in size through decimation if required, are then instantiated in the mixed reality environment, ready for visualization and alignment. To quickly reach specific areas of the installation, the application provides rough tuning controls for positioning. Using the joysticks of the Meta Quest controllers, operators can apply large translational or rotational movements of the model. Recentering is based on 4 reference points, 2 selected on the virtual model and 2 on the real installation. The vectors defined by these pairs are used to calculate the rotation, while the resulting translation aligns the model with its physical counterpart. This process establishes a correspondence between digital and real structures, preparing the system for the subsequent fine adjustment. After recentering, a fine adjustment stage ensures full coincidence between digital and real structures. The application provides rotational and translational controls, accessible through a virtual tablet attached to the operator's hand. Rotation can be applied around a selected pivot point with angular steps ranging from thousandths of a degree to 2 degrees. Moreover, translation allows displacements along the 3 axes with increments from 1 mm up to 10 centimeters. The system also includes measurement tools for dimensional verification. By selecting 2 points in the scene, the distance is immediately calculated and shown in the interface. Finally, in real assembly scenarios, the application enables operators to interact with individual components of the installation, such as pillars or shafts. By selecting these elements, references and labels can be displayed, making it possible to identify parts and verify critical dimensions, for example, the height of a support or the distance between structural elements. The XR-DIVIN project demonstrates how mixed reality can enhance dimensional verification in industrial assembly, reducing errors, saving time, and supporting operators with an intuitive and reliable tool.